So we were discussing electric potential energy due to a system of three charges. Already हमने electric potential energy due to a system of two charges को लिखा और उसको हमने कितना लिखा electric potential energy due to a system of two charges EU is equal to 1 upon 4 pi epsilon naught और two charges हमारे पास थे Q1 and Q2 and distance was R. So this was in Joule. This was in Joule. So this was the electric potential energy due to the system of two charges. So now our today question is electric potential energy due to a system of three charges. So let me take three charges which are placed at the three vertex of a triangle. So first charge is Q1, this is plus Q1, and this is minus Q2, and this is plus Q3. Three charges placed at three corners of the triangle. And the distance between these two, it is, let me take it is R12 because the charges are 1 and 2. And it is R13 and it is R23. So find the total electric potential energy of this system of three charges. So we have to find total or net potential energy of the system. So very easy. So here I will find out the potential energy due to these two charges. So let me take that is V1 and let me take this is V2 and let me take this is V3. So first I will find out, so the total potential energy that will be equal to V1 plus V2 plus V3. So one by one we will find out V1, V2, V3 and we will place the values of V1, V2, V3. Sorry, it is potential energy, not the potential. So call it U2, call it U1, call it U3. So we are taking potential energy, not the potential. So U1 plus U2 plus U3 and the sum of the three that will give the U, the total potential energy. So first I will find out U1. So U1 is equal to 1 upon 4 pi epsilon naught and we have Q1 and minus Q2. So this is minus Q2 and the distance is R12. So this is equal to minus 1 upon 4 pi epsilon naught Q1 Q2 divided by R12. Similarly, we can find out U2. So U2 is equal to 1 upon 4 pi epsilon naught and it is Q1 and Q3, Q1 and Q3 and both the charges they are positive and the distance is R13. Similarly, U3 is equal to 1 upon 4 pi epsilon naught. So one is minus Q2 and then other is Q3 and the distance is R23. So it can be written as minus 1 upon 4 pi epsilon naught minus 1 upon 4 pi epsilon naught Q2 Q3 divided by R23. So put the values of U1, U2, U3 in this first equation. So I will get the total energy, total potential energy is equal to 1 upon 4 pi epsilon naught. This is minus Q1, Q2 divided by R12. Second is 1 upon 4 pi epsilon naught Q1, Q3 upon R13 and then minus 1 upon 4 pi epsilon naught Q2, Q3 divided by R23. So you see 1 upon 4 pi epsilon naught is common in all the three potential energies. So we can take this outside. This is common. So we can take this outside. So U is equal to 1 upon 4 pi epsilon naught. It is outside. So what is inside? Minus Q1, Q2 divided by R12 plus Q1, Q3 divided by R13 and minus Q2, Q3 divided by R23. So this is the total potential energy due to the system of three charges. So we can find out the total potential energy of a system of any number of charges. That's very easy. That's very easy. We can solve it for any number of charges. So now I will go to the next topic, which is called potential at a point due to axial line and due to equatorial line. The same topic we have studied in the electrostatic when we find the electric field due to a dipole on the axial line and on the equatorial line. Now, in the chapter of potential, we will find the potential due to a dipole on the axial line as well as on the equatorial line. So this is the topic of our today's discussion. And I already told you that potential that is charge dependent. For positive charge, potential is positive, and for negative charge, potential is negative. So let me start. So potential at a point. So potential at a point on axial line, axial line means x-axis, due to a dipole, very simple topic, but very important topic, due to a dipole. Potential at a point on axial line due to a dipole. So let me take a dipole. So dipole is a system of two charges, minus Q and plus Q. So here I have plus Q. And the dipole length, it is 12. Already we discussed in the case of electric field intensity, the length of the dipole is 12. So each side is L because the length is taken from the center of the dipole, the center of the dipole. So the distance of minus Q from the center of the dipole is L. Likewise, the distance of plus Q from the center of the dipole is L. And let me choose the point on the axial line. So this is my axial line, means x-axis, and on this x-axis I will choose a point P where I will find the potential. So because two charges are there, so one potential I will have due to minus Q charge and other potential I will have due to positive charge. So for minus Q charge, the potential that will be negative potential, and due to plus Q charge, the potential will be positive. So I am interested in the total potential at this point. So let me take the distance of this point P from the center of the dipole. It is taken as R. This is R. So now I can find what is the distance of this plus Q charge from this point P. So I can find out this distance. So distance of this plus Q from point P. So that will be R minus L, R minus L, because this total distance from the center is R. So if we subtract this L, so this becomes the remaining distance R minus L. Now, what is the distance of minus Q charge from the point P? So that is so easy, it becomes R plus L. it becomes R plus L, because up to here it is R and then it is L. So this becomes R plus L. So first I will find out potential due to plus Q charge, and here I will find the potential due to minus Q charge. So let me call for potential due to plus Q charge is positive and potential due to this charge is negative, or we can call it as V1, or I can call it as V2. So the total potential, I know that that will be equal to V1 plus V2. So हम V1 और V2 को पहले calculate करेंगे. So V1 is equal to, we know it is 1 upon 4 pi epsilon naught, and the charge is plus Q charge. So this is my plus Q charge, and the distance of plus Q charge from the point P, it is R minus L. So it is R minus L. It is R minus L. Now I will find out V2. So V2 is equal to 1 upon 4 pi epsilon naught. And here we have minus Q charge, and distance of minus Q from the point P, it is R plus L. So this is V2 is equal to minus 1 upon 4 pi epsilon naught Q upon R plus L. Now place the value of V1 and V2. So we will find out the total potential. V is equal to, so I can take this 1 upon 4 pi epsilon naught outside. Oh, okay, I will take it outside, and this is Q upon R minus L, and then plus, and this is now it becomes minus, because the second potential is negative. So this positive is replaced by a negative sign. So we will take the negative sign over here. So this is negative, and Q upon R plus L. Even we can take this Q also outside. So let me take this Q also outside. This Q also outside. So what I have, I can take this Q outside. So this Q is outside. So it is 1 over 1 over. Now the total potential V is equal to Q upon 4 pi epsilon naught. Now we can solve this. So this becomes R square minus L square, R square minus L square. And this becomes R plus L minus R minus L. Now we will open this bracket. So 4 pi epsilon naught, and this is R square minus L square, and this is R plus L minus R plus L. So R is cancelled. So what is left? V is equal to Q upon 4 pi epsilon naught, and this becomes L plus L, 2L, 2L R square minus L square. Now focus on the numerator, it is Q into 2L. And in case of dipole, we know that in case of dipole, Q into 2L, charge multiply, that is called dipole moment P. Dipole moment P. So now V is equal to 1 upon 4 pi epsilon naught, and this becomes dipole moment P divided by R square minus L square. So this is the total potential on the axial line due to a dipole. Now let me take one special case. And the special case is that if the length of the dipole is very small as compared to distance of point P from the center, means R is much greater than the 2L. So it means R is much greater than L. So length of the dipole बहुत छोटा है, but जो point P है वो comparatively large distance पे है. So in that case I can just ignore this L. So L को ignore करेंगे. So what is left? That is V is equal to 1 upon 4 pi epsilon naught. P is the dipole moment and divided by R square. So now it's a very special case. And in this case of dipole, V is inversely proportional to R square. In our all earlier cases of potential due to a single charge, the potential was inversely proportional to, for a single charge, the potential was inversely proportional to R, but for a dipole, the potential is inversely proportional to R square. Okay, so this was potential due to a dipole on the axial line. So likewise, we will find out the potential due to a dipole on the equatorial line. So let us solve for that. Equatorial line, it is also called right bisector. Right bisector. So we are interested in finding potential at a point at the right bisector. So it is called potential at a point on equatorial line due to a dipole. Due to a dipole. So let me take a dipole, which is a system of two charges. One is positive, other is negative. So let me take a point Q, charge at point A, and plus Q charge at point B. So now this is my dipole, and the length of the dipole is 2L. It is 2L. So let me take this center, and so this length is L, and again this length is L. And from the center, I draw a perpendicular, and I choose a point P, which is at a distance R from the center of the dipole. So we will find the potential at this point P due to this positive charge, and potential at this point P due to the negative charge. So let me join these two sides. So now at this point, the potential due to positive charge, and at this point, the potential due to negative charge. So let me take the potential due to positive charge is V positive, and let me take it is equal to V1, and potential due to negative charge, it is V negative, or it is the V2. See the total potential at this point P, V is equal to, that is the sum of V1 plus V2. So let me find, so call this equation as 1. So first I will find out V1. V1 is the potential due to the positive charge. So that is equal to 1 upon 4 pi epsilon naught, and this is plus Q charge, and the distance of the point P from B, you can take it as PB. So it is, you take it PB or BP. So call this equation number 2. Now I'll find V2 due to negative charge, and it is equal to 1 upon 4 pi epsilon naught minus Q upon, and it is AP. It is AP. So the total potential, call this equation, so V2 is equal to minus 1 upon 4 pi epsilon naught Q upon AP, and call this equation 3. Now put the value of equation 2 and 3 in equation 1. So we will get V is equal to 1 upon 4 pi epsilon naught Q upon Bp, and this is now it is minus 1 upon 4 pi epsilon naught Q upon AP. So the total potential V is equal to, take this 1 upon 4 pi epsilon naught common. It is common in both the terms. So we can take it as common 1 upon 4 pi epsilon naught. Even we can take this Q also outside. Q also outside. So what is left? 1 over Bp minus 1 over AP. Now see carefully. This is the isosceles triangle. AP is equal to BP. So AP is equal to BP. So this term is cancelled out. So the potential becomes equal to 0. So at the equatorial point, the potential is 0. So the potential is 0. Potential is 0. What it means? It means that electric potential is everywhere 0 on the equatorial line. So on the equatorial line, electric potential is 0. But electric field intensity is not 0. इलेक्ट्रिक फील्ड इंटेंसिटी ऑलरेडी हमने इक्वेटोरियल लाइन पे इलेक्ट्रिक फील्ड इंटेंसिटी निकाली है, वो 0 नहीं है, पोटेंशियल 0 है, इलेक्ट्रिक फील्ड इंटेंसिटी 0 नहीं है, बट पोटेंशियल 0 होने के कारण वी कैन से नो वर्क इज डन इन मूविंग ए चार्ज अलोंग दिस लाइन. सो अगर हम किसी चार्ज को यहां से सपोज वी प्लेस ए टेस्ट चार्ज ओवर हियर, और उस टेस्ट चार्ज को हम यहाँ पे इस लाइन पे कहीं मूव कराते हैं, चाहे डाउनवर्ड मूव कराएं चाहे उसको अपवर्ड मूव कराएं, सो इस लाइन के ऊपर कहीं भी अगर हम उसको मूव कराते हैं, सो वर्क डन इज इक्वल टू 0. वर्क डन इज इक्वल टू 0. सो इक्वेटोरियल लाइन पे किसी भी चार्ज को मूव कराएंगे, सो वर्क डन 0 होगा, कोई वर्क होगा ही नहीं, क्योंकि पोटेंशियल 0 है, इलेक्ट्रिक फील्ड 0 नहीं है. पोटेंशियल 0 होने के कारण वर्क डन 0 है, बिकॉज पोटेंशियल इज इक्वल टू W upon Q naught. So when potential is 0, then work done in taking a test charge, that is equal to 0. So कोई वर्क हमें यहाँ पे करना नहीं पड़ेगा. So हमने दो चीजों को डिस्कस किया. एक डाइपोल के कारण एक्सियल लाइन पे पोटेंशियल कितना होगा वो हमने डिस्कस किया, और हमने पाया कि पोटेंशियल इज इनवर्सली प्रोपोर्शनल टू आर स्क्वायर, जबकि एक सिंगल चार्ज के केस में पोटेंशियल वाज इनवर्सली प्रोपोर्शनल टू आर. बट हियर इन द केस ऑफ ए डाइपोल व्हिच इज ए कॉम्बिनेशन ऑफ टू चार्जेस, पोटेंशियल इज इनवर्सली प्रोपोर्शनल टू आर स्क्वायर एक्सियल लाइन पे. बट इक्वेटोरियल लाइन पे तो पोटेंशियल 0 आया है ना. ऑलरेडी हमने निकाला है इलेक्ट्रिक फील्ड इक्वेटोरियल लाइन पे 0 नहीं है, बट पोटेंशियल 0 है. अब पोटेंशियल 0 होने का फिजिकल सिग्निफिकेंस क्या हुआ, बिकॉज वी नो दैट V इज इक्वल टू W अपॉन Q नॉट. अगर पोटेंशियल 0 है तो वर्क डन भी 0 होगा. इसका मतलब ये हुआ कि इक्वेटोरियल लाइन पे किसी टेस्ट चार्ज को अगर मूव कराते हैं अप एंड डाउन, सो हमें कोई वर्क एक्सटर्नल वर्क करना ही नहीं पड़ेगा. सो दिस इज ऑल अबाउट द potential on the axial line due to a dipole and potential on the equatorial line due to a dipole. So we have a next topic which is called the equipotential surface, but we will discuss the equipotential surface in our tomorrow lecture. So how the equipotential surfaces are created and how they are helpful in the physics. So we will discuss that in our next lecture. So let me take the attendance. Anjali and Khushi, okay, both of you? So
thank you.
Rest of the lecture or the equipotential surfaces and their properties we will discuss in our next lecture. Okay Anjali, okay Khushi, bye.
Thank you sir.
Okay.